Moving on to chapter 6 today. We're going to start talking about normal curves and sampling distributions. 6.1, graphs of normal probability distributions. So let's review some distribution shapes we learned in the previous unit. Remember, we have something that's called symmetrical. And so I'm just going to kind of build it my inside out, kind of like that. And so if you were to draw a curve over those bars, kind of looks like this. Not a great artist. And all right, symmetrical underneath it. And so this is a normal curve. This is what we consider a normal curve, and we'll be talking a lot about in this unit. So the area under the curve is what we'll be working with in chapter 6. So I'm going to go ahead and write, this is a normal curve. A lot of times we call it a bell curve. And we're going to be talking a lot about the area under the curve. But let's also review some other shapes that can happen even in this unit, but most of the time, we're referring to the normal curve. Okay, so if we have something like this shape, remember the curve would kind of look like this, which would be skewed left. It's like my pen's about to die on me. Then we would also have like the skewed right curve, which would look kind of like this. So go like this, and then it slides down on the right, so we call that skewed right. All right, let me darken my words because my pen died. All right, skewed right. Then we have the uniform one where it's all exactly the same. And it kind of looks like this. And then we have bimodal. Remember, bimodal is just maybe you have two high towers and some randoms in between. So you got like a high tower, a low tower, or two, maybe another high tower and a low tower, maybe on each side, something like that. So bimodal kind of makes a fun shape. Looks a little bit like an M. So the normal distribution is one of the most important examples of a continuous probability distribution. A normal distribution graph is called a normal curve. Or we also refer to it as a bell-shaped curve. Let's turn the page. Oh, I probably should put uniform underneath this one, right? Didn't label that graph. Hopefully you did as I said it. And I'll darken those up just a little bit. Okay. Excuse me. So characteristics of a normal curve. It's going to be bell-shaped with the highest point over your mean. That's your mu symbol. So remember, that's your average or your mean. So the middle part of each of these will represent the mean of whatever data you're working with. It's symmetrical. Curve approaches the horizontal axis, but never ever touches it. Inflection points between cupping upward and downward occur above your mean plus 1 standard deviation and your mean minus 1 standard deviation. Excuse me, the area beneath the curve and above the axis is exactly 1 or 100%. So if you're looking decimal form 1, or if we're talking about percentages, 100%. The area represents a probability. And so to kind of picture some of the things that were stated in that, I am not the best artist and I will never ever claim to be, but here's my bell-shaped curve. And so down the middle is always going to be your mean. And then they say, and this again is not the best graph, but your inflection points, meaning where it's starting to turn, is always your mean plus whatever the standard deviation is. Or, and this is an inflection point, your mean minus 1 standard deviation. And so these little stars are my inflection points. The area underneath this curve, like we mentioned, is 100% or 1. And so if you had a highlighter, you know that they're meaning everything under here, the area, that's what that represents in those probabilities. So let's take a look at examples of normal curves. Notice this one's kind of fat. You know, a normal curve doesn't have to be super fat. These are both considered normal curves. They're symmetrical. If you noticed, if you were to fold them, the lines would meet up on the other side. And so these are examples of two different normal curves. The straight line represents 52 miles per hour with a standard deviation of 7 miles per hour. And then the flatter line is 52 miles per hour with a standard deviation of 12. So you can kind of tell the standard deviation when it's smaller is makes the curve tighter. Let's go ahead and turn the page. So we're going to sketch a normal curve with the mean of 2 and a standard deviation of 5. So we're going to maybe draw your baseline, and then this is not a great curve, but I already did it, so we're going to go with it. So I would say that this would be about the middle, assuming this was symmetrical and I was a great artist. So our mean is a 2, is what that means. And if we were to go over 1 to the right, this represents your mean plus 1 standard deviation. And they said our standard deviation is 5. So that's like saying 2 plus 5 is 7. And then to the right of that would be your mean plus 2 standard deviations. I had to get a little bit smaller in my writing for that one. And so if I were to take our mean, which is 2, plus 2 times 5, that would give us the number 12. Or you could think you're adding 5 each time as you move to the right. And then we're going to do one more, and this will be your mean plus 3 standard deviations. And again, this is like saying 2 plus 3 times 5 is 15, plus 2 is 17, or again, just add 5. So each of these areas are always going to constantly represent a certain percentage of the space under the curve. So this will be 34%. To the right of that is going to be 13.5%. And I will draw this actually on another page in a minute. So that says 13.5%. This one would represent 2.35%. And then anything in the what we call the tail is 0.15%. Now, this is the right-hand side. And so the left-hand side just means we're doing the same thing, but you'd be subtracting the standard deviation. So you'd say mean minus the standard deviation. So 2 minus 5 is a -3. So it's kind of like a number line. You're going to have negatives working its way to positives, or smallest to greatest. This area matches the mean plus a standard deviation, so it also represents 34%. Then when we draw here and we say mean minus 2 standard deviations, we would get -8. And then one more, the mean minus 3 standard deviations, we would get -13. And then the space again. So when you go 1 standard deviation over, each of those little sections represent 34% of the data under the curve. When we make our way out, these two represent 13.5%. This represents 2.35%, and the tail is 0.15%. So these are referred to as tails of the curve. And it represents a very small percentage of the data. So if we were to total from 1 minus the standard deviation to 1 plus, the total amount of area underneath there is 34 plus 34 is 68%. So 68% of the data falls underneath the mean plus 1 standard deviation. If we were to total between 2 standard deviations from here to here, the percentage under that curve is now 95% of the data. So you're adding all 4 of those sections together to get that. And then from 3 standard deviations, I should have used my blue pen, but 3 to 3, that's 99.7%. So that's going to help us answer the following. So this is called the empirical rule that we just learned about the different percentages. We just happen to give some numbers to help us understand the bell curve to go with it. Your mean can always be any number with a standard deviation of any number, and that's how you will complete a bell curve representing the empirical rule. So approximately 68% of the data values are within 1 standard deviation. 95% of the data values are within 2, and 99.7% are within 3 standard deviations. Each end, we call the tail of the normal curve, contains approximately 0.15%. Now, that's each curve. That's not totaling them together like we did the other areas. If we totaled them, then that would be like 0.30 total. Right, so if 3 standard deviations represented this, and then you added the tails, both of them to it, that represents the 100% that we're talking about under the curve. Use the empirical rule to answer the questions. Draw the curve, shade, and calculate how much of the area or probability under the curve is between the vertical lines. So if we drew the empirical rule, if we drew a bell, just to represent this is just very basic standard. They're not giving us values for it, but this is representing your mean right in the middle. And then it's saying between the mean and 1 standard deviation. And so it wants us to shade it. So I'm just going to maybe put some lines to represent this area. And what we learned from the empirical rule on the page before is that this represents 34%. So the area would be 34%. If they ask probability, you put it in decimal form and you would write 0.34. This one wants to know the area between the mean minus 1 standard deviation. So, and the actual mean. So you need to pay attention. That's what it's looking for. You can draw the entire bell curve information that we did on the previous page, but don't really have to, because again, this is the mean right in the middle. And then this time we're just to the left. but it still represents just 34% of the data that would be underneath that section of the bell curve. Now, if we were asked to find the area between our mean plus 2 standard deviations, so that's 2 places. So this is our mean plus 1 and our mean plus 2 standard deviations. Remember, this would be 34%. And this is, here, I'll write it like this, 34%. And then this area was 13.5%. So to find our area, we need to add those 2 sections together because they asked us to shade it. So here's my shading. We drew our sketch. We drew the space that they were talking about. For the area, you'd be adding 34% plus 13.5%, which equals 47.5%. Remember, probability is just turning those into decimal form and then adding them together, which would be 0.475. This one wants you to do it between your mean and minus 3 standard deviations and the mean. So here's the mean. Here's 1 standard deviation. Here is 2 standard deviations, and here is 3. Kind of have to squish it in there when you don't have a lot of space. So remember, this represents 34. This is 13.5. And then this is 2.35. So this is the space that we're shading. I did go ahead and kind of write the area underneath, but that just means we're adding 2.35 plus 13.5 plus 34%, and we get 49.85% when you add that together. Decimal form would be 0.4985. Now, it's not always asking from the mean. If you noticed, questions A through D was basically, we kind of use mean in the middle as the guideline, but this time we're going from -1 standard deviation to 2 standard deviations. So just draw what it's representing. So this is our mean, and this is our mean minus 1 standard deviation. And then this one, we're going over to a positive to the plus 2 standard deviations. So remember, this is 34, 34, 13.5 are our sections for those 3. So from here, this is -1 standard deviation to the mean, over to 1 standard deviation, then over to 2 standard deviations. So we're adding those areas together. So 34 plus 34 plus 13.5% will give us 81.5%. If they ask the probability of that, it's just the decimal form of those same numbers. And then the last one, when my bell curve keeps getting kind of worse every time. So our mean, and then we're going to go, I start at the mean just as a habit, but we're not doing this one from the mean. We're doing it from 1 standard deviation, and this one is 2 standard deviations, and this one is 3 standard deviations. So remember, we're not finding the area here. We're starting at 1 standard deviation and finding the area between these 2 only. So this is 13.5%. And then this section is 2.35%. So our area, we are adding 13.5% plus 2.35%, and we get 15.85%. Probability is turning that into decimal form. So hopefully that kind of gives you an idea of what we're talking about with the empirical rule. I would like to just turn this over on the back of this page and just kind of add a section. So, and maybe even turn my page horizontal to do this. So your empirical rule, just in review before we move on to and do a little bit more, is you're going to have a bell-shaped curve. And these areas are standard with all curves, or they say they are. I mean, and they are. My picture, it's the reason why I say it kind of like that, is not perfect. So the area is not going to look to scale by any means. So we're going to go over one standard deviation. We can go over two standard deviations, and we can go over to three standard deviations. So if we just called the mean 0, for instance, to make it easy, and if we had a standard deviation of just 1, then that means, you know, this would just go up kind of like a normal counting line. But it also helps us understand 1 standard deviation, 2, and 3. And then we do the same, but we go minus, so that'd be -1. So our mean minus 1 standard deviation, our mean minus 2 standard deviations, and our mean minus 3 standard deviations. And so we will always represent from mean to 1 standard deviation over 34% on each side. So as a total, that's 68%. I know I'm kind of repeating the lecture, but it's a very important part of this unit. And then if we go over to 2 standard deviations, this section only here is 13.5%. And that's also when we minus 2 standard deviations. And then these two sections that we have are 2.35%. I was about to repeat my 1 standard deviation. And then these are considered tails after that, and they say 0.15%. So a very small percentage in the tails. So as a whole, that's just a review over the empirical rule. These are set values that happen all the time. They never change. So we're going to turn and answer some application problems dealing with the empirical rule now. All right, the yearly wheat yield per acre on a particular farm is normally distributed. You're going to read that a lot, but it is a keyword later. Normally distributed with the mean of 35 bushels and a standard deviation of 8. So they ask us to draw the curve and shade the area under the curve that represents the probability that an acre will yield between 19 and 35 bushels. So let's draw what they're saying. Since we now understand the empirical rule, we can represent this with this image. So our mean, they tell us, was 35. And if we add 8 to that, that would be plus 1 standard deviation, we would get 43. If we add 8 to that again, we're going to get 51, and then add 8 to that, we get 59. So remember, this would be 1 standard deviation, 2, and 3. And so then right here, we're going to subtract 8 from 35. So we get the number 27. Subtract 8 from that 19, or from 27, we get 19, and then subtract 8 from 19, we get 11. But it asks us to find the area under the curve that represents the probability of 19 bushels to 35 bushels. So we're talking about this area between those two lines. And so this is my shading. If you have a highlighter and you want to do a better job shading, go ahead. So this is 13.5%, if you remember from the other page, and this is 34%. So if it says it just said draw the curve and shade the area under. It didn't tell us to identify that area yet, but we do a little bit later. So we'll come back to that and answer that. It says, part B says, is the area the same as the area between your mean minus 2 standard deviations? So remember, this would be like, this kind of helps if you do it like this too. So you can see the different deviation, the standard deviations. So is it the same between minus 2 standard deviations and the mean? Yes, that's the space that we're talking about. That's all that's really asking. So we would say yes, that area is the same. If you didn't have those numbers, that area is the same that represents it with this application problem. So it says use the drawing to find the percentage of the area between the 19 and 35 bushels. So we would add 13.5% plus 34%. So our area would be 47.5%. And if it asks for area and not the probability that something is going to land between that, then that's all you do. You answer it in percentage form. But then this one says, what is the probability? So that's a decimal form, that the yield will be between 19 and 35 bushels. So that's going to be that same space that we talked about. So the way that you could write this as a probability, or you might see it, is to say from 19 bushels less than or equal to X, which is less than or equal to 35. So this represents that space up there that we're talking about in the empirical rule curve with our values shaded up there. So if we added those numbers in decimal form, it would be 0.75. So it's really talking about the same thing. It's just how you might read it when you're answering it in percentage form or decimal form. Turn the page. The amount of coffee dispensed by a coffee vending machine normally distributed. So we're talking about our bell-shaped curve with our percentages that we've learned about, with a mean of 7.6 ounces and a standard deviation of 0.4 ounces. Draw the distribution. So again, here's my curve. It's getting worse and worse and worse as we go. It's kind of skewing, but let's pretend that that's a perfect symmetrical graph, please. So remember, this would be like your mean, your +1 standard deviation, your +2, and your +3. This would be like -1, -2, and -3. But we're going to actually use real values that were given to us about the coffee. So they're saying the mean is 7.6 ounces with a standard deviation of 0.4. So we're going to add 0.4 each time we move over, would be about the easiest way to do that. So this will be 8. And then if we add 0.4 there, it'd be 8.4. And if we add 4 there, it'd be 8.8. Since my graph is kind of tight, I'm kind of trying to get it all in there. If I were to subtract 0.4, this would be 7.2, this would be 6.8, and this would be 6.4. So these are the values that you would have that's representing the mean and then as you're moving up to 1, 2, and 3 standard deviation or down. So it says find P, meaning the overflow of an 8-ounce cup. So let's think about what that means. This is an 8-ounce cup. That's what these represent. And we're going to overflow it. So anything more than 8 ounces is to the right of that 1 standard deviation and all the way to the end, including the tail. So if we're finding the probability of that, remember this is the 34%. This is your 13.5%. This is your 2.35%, and this is your tail of 0.15%. So we're going to be adding those since they're finding the P, the probability of it. We're going to be adding 0.135 plus 0.0235 plus 0.0015. So you still have to move that decimal 2 places to the left, making it a very small decimal form. And so the probability of that would be 0.16. And then part C says find P won't overflow. And you could probably do this 2 ways. You could shade this section and add them, or we could use that complement of it. Remember where we just say the probability that it won't overflow? I could say, well, that's just taking 1 minus the probability it will overflow. And so I think it's a little bit quicker if you do it that way. But as long as you understand that won't overflow, we're talking about this section now. That's adding all of that section together if you want to do it that way, is the won't overflow. That means it would be less than your 8-ounce cup. If there are 850 cups, how many do you expect, coming back, this is a keyword from your last unit, how many do you expect to overflow? So this is where we're taking the number of cups times the probability that we just found above that it would overflow. So we're saying 250 cups times the probability that it would overflow, that's what we're calling favorable, is 0.16. So we're going to do that in our calculator, and that's 136 cups. So it'll continue to build on concepts all through each unit. We'll keep using that concept we learned in the previous unit. Assume normal distribution. Doug scored a 57 on the Miller Analogies test, which has a mean of 50 and a standard deviation of 5. Jennifer scored a 120 on the WISC intelligence test, which has a mean of 100 and a standard deviation of 15. Compare the score. Who had a better score? And so we're not going to be able to really answer who had a better score. It leads us into our next unit. But I want to show you what this means now. So if we're talking about Doug, and I just want to show you how we can't really totally compare it exactly yet. And we're going to learn a new concept in 6.2. So we can really compare things between people by using our empirical rule. By using our bell-shaped curve. So it said Doug scored a 57 on the Miller's analogy test, which had a mean of 50. So right here, we're going to do our 50. And a standard deviation of 5. So this would be 1 standard deviation, 2 standard deviations. So that's going to be somewhere past 55. So we're not going to have an exact number until we learn something from the next unit to help us understand how how to compare Doug and Jennifer. So let's go ahead and just draw this though for now so you can look at it. So we're saying that his score, which is going to be our X value later, going to go ahead and write that down, is 57. His mean was for this test is a 50, and the standard deviation was a 5. I just kind of want to write some givens so it's already there. Jennifer, she did a different test, and the mean of that test is a 100 with a standard deviation of 15. So one standard deviation of 115, and then we do another standard deviation of 130, and we could go on to 3 standard deviations, but it said she had a score of 120. So again, that's not exactly on one of those 1 standard deviation or 2 standard deviation lines. It's kind of right here. And if you're looking at kind of the pictures, it looks like they really scored almost identically, right? And actually, it's not exactly identically. We are going to learn how to find what's called a z-score. So I hope you have your table printed out and ready when we start the next lecture. Pull that out from the back part of your notes. But we're going to be working with what's called a z-score to get a more detailed comparison of Doug and Jennifer. And so I'm writing this information down again, just so it'll be here. So Jennifer scored, the X value is 120. Her mean, the mean score was 100, and the standard deviation is 15 for her. So again, just kind of looking at those pictures of what we know about the empirical rule, they look like they scored approximately at about the same standing.